My esteemed listeners, this tutorial brings out the efficiency analysis of algorithms part 4, and in this tutorial we will discuss about recursive algorithms. Before we take on to analysis of recursive algorithms, we will see where exactly the situations where exactly a recursive solution to problems would arise. You consider this example over here. This algorithm determines the number of bits required to represent a decimal number n. Okay, and the algorithm is written for this. Okay, and it simply works. There is no doubt about it. And we should notice that the most frequently executed operation here is not inside the loop, but it is in the while loop. It is in the heading of the while loop, because there the number of comparisons depends upon n becoming greater than 1. Since the number of times the comparison will be executed is larger than the number of repetitions of the loop's body by exactly 1, the choice is not that important. A more significant details of this algorithm will be made well known to you by discussing this. Let us consider the decimal number to be 15. And number of bits equal to 1. Anyway, to start with, number of bits equal to 1, decimal number is 15. N is greater than 1, therefore it will enter into this loop, control will enter into this loop. So number of bits will become 1 plus 1, earlier 1 and now 1. Number of bits here serves like an accumulator. N will be hard now. N will be hard and the floor of the value is taken, therefore 15 by 2 is 7, equal to 7, because that is a floor value is taken. And once again it will go, n is greater than 1 surely, therefore number of bits will become 3, 1 will be added, and 7 by 2 will become 3, okay, and it will enter into the loop because n is greater than 1, so number of bits equal to number of bits 1 plus 1, so it becomes 4. And once again further 3 will be divided by 2 and the floor value is taken, it becomes equal to 1. But anyway, the while loop has to go if and only if n is greater than 1. Therefore it will stop and it will return number of bits. Anyway, 4 bits are required in order to represent 15. Okay, this comes from a simple fact that 15 is divided by 2. Okay, 2 sevens are 15 and 1 remains over here as a reminder, and 2 3s are 6 and 1 remains over here, and 2 1s are 2. Okay, and what remains is here is 1, and 1 cannot be further divided because it should be greater than 1. In order to divide by 2 it should be greater than 1, therefore 1 2 3 4 bits. Okay, this particular algorithm is written exactly simulating the kind of operations that is to be done. Now every time the algorithm would stop. The algorithm is unambiguous, all these things are there, all the features that is required for a well written algorithm is very well written over here. But anyway, we cannot afford to calculate how many times this division happens. Because we don't know the value of n. That is number 1. Number 2, in every iteration this number gets hard. Okay, it doesn't increment by 1 like any other algorithm, non-recursive algorithm, or any other iterative algorithm. Okay, or it is not lessened by 1 also. Okay, anyway, the number is going to be hard in repetitive cycles. Therefore this kind of problems are amenable to be written under recursive category. Okay, these problems should be addressed in a recursive way. Okay, so there are some problems where number of iterations is bound by the condition. Okay, it is condition bound, and the input is okay, it will be decreased iteration by iteration, not sequentially, not incrementally. Rather there will be a big increment or maybe a big decrement. Therefore in such cases we cannot count the number of basic operations that gets executed by putting sigma, because we don't know the lower limit and the upper limit and how exactly it decrements or it lessens, the input goes on lessening, okay, that cannot be determined over here, and exactly it is not happening that way also. Therefore these kind of problems are amenable to be written under recursive category, recursive problem solution. Okay, anyway, recursive problem solution, okay, problem solution to recursive kind of a problem, okay, will be something like this. We can take an example of this factorial only. Okay, look at this. The function, the factorial value of a number integer n can be expressed as, it is a function anyway, function of n, factorial function n can be expressed as f of n minus 1 into n minus 1 into n. Yeah, this is the thing. For all n values greater than 1, because factorial of n equal to 0 is 1. Okay, for all the values of n greater than 0. So therefore recursive functions will be expressed in terms of their functions only at a different input point. Preferably in almost all the problems, the definition of the function by itself goes with a lower value of the input. Once again this can be written, okay, this can be exemplified further. This f of n minus 1 can be written as f of n minus 2 into n minus 1 into n, like this, and I can also write once again for f of n minus 2 as f of n minus 3 into n minus 2 into n minus 1 into n. Therefore this is an example of single recursion. Okay, single recursion always grows like a chain. Okay, single recursion grows like a chain, and there are some problems, okay, in reality, that they should be solved only recursively. Okay, therefore recursive problem, whether the problem is to be solved recursively or non-recursively, lies in the problem itself. So it is in the hands of the algorithmist to determine whether the solution can be offered in a most recursive way. So before we analyze this recursive algorithm that we have written for a simple problem like factorial of a number, we should be able to differentiate between a recursive algorithm and a non-recursive algorithm, or recursive function and a non-recursive function. Therefore recursive program and a non-recursive program. In a recursive program, in a non-recursive program, for example, there is a well-defined looping construct. Okay, there will be a well-defined looping construct, but in a recursive algorithm or in a recursive function or in a recursive program, there is no such well-defined looping construct, because function is repeatedly applied, okay, till the input becomes a too less a value where the solution is available. Therefore the function, it is as if function is calling itself. Function is repeatedly applied for itself at a reduced input point, of course, at a reduced input point with a lower bound. When n becomes equal to 0, you go on reducing this input value. When n becomes equal to 0, you found the solution, f of 0 equal to 1. So that's how it goes. Okay, there is a looping constraint and there is no looping construct. Okay, and non-recursive function implementation in computers doesn't need any stack. No stacks is required. Okay, but here for a recursive function, stack is required. Of course, the operating system should press stack into use. Okay, and for non-recursive function, there is no base case. Of course, there is no base case. Okay, there is no base case as far as non-recursive function is concerned. For a recursive function, base case decides as to how many times the function is to be called again and again. Base case means it is the input size, or it is the input value at which function ceases to be applied again. Function ceases to be applied again, or function will bring in a known value. For example, f of 0 here equal to 1. Okay, these are all the salient differences between non-recursive function and recursive function. Okay, now we have this over here. We will try to solve this, right? We will try to analyze this, and we will develop as to how we can develop the efficiency case of this recursive algorithm, namely finding factorial of a number. Okay, finding factorial of a number. Right. Now, any recursive algorithm can be analyzed not under the framework of analysis of algorithms that we discussed for non-recursive algorithms. Okay, a framework of analysis of algorithms comes with only two steps, that is, we have to determine the input size, then we have to find the order of growth. But here those two steps cannot be applied, since simply because the second step cannot be done meticulously over here, cannot be done accurately. We cannot determine order of growth of a recursive function. Therefore, there is another way. The other way is you have to frame what is called as recurrence relation. Okay, by going through any recursive algorithm, we need to develop what is called as recursive relation or equation of recurrence or recurrence relation. Okay, recursive relation, we will say it as recursive relation or equation of recurrence or recurrence relation. Anything will hold good. But anyway, so here we can write like this. The basic operation is multiplication. How many times this multiplication is done, we don't know. We will write it in the form of a recursive explanation, recursive expansion. So number of multiplications that is needed in order to find factorial of n, number of multiplications which is needed in order to find the factorial of n, equal to number of multiplications that is needed in order to find factorial of n minus 1. We don't know. We will just write it like this, recursively only. Okay, plus 1 multiplication before the function is called. I repeat, number of multiplications required in order to find factorial of n equal to number of as many multiplications as it is needed in order to find out factorial of n minus 1 plus 1 multiplication before the function is called. Okay, and the base case is m of 0, because if the input is 0, there is no multiplication, because the function will return the answer directly, because it is written over here, if n equal to 0, it will return 1, and there is no multiplication involved over here. Therefore, and if we solve this recurrence relation for any recursive program, recursive function, recursive algorithm, therefore, okay, we need to develop recursive relation first, and then we need to solve the recurrence relation. If you solve the recurrence relation, then only we will be definitely arriving at the basic efficiency case. Okay, there are two methods, of course, in order to solve such a recurrence relation. One is the backward substitution. Okay, backward substitution. The other one is substitution. I will write only this much. And the second one is Master's theorem. Okay, Master's theorem can also be applied in order to solve the recurrence relation, but Master's theorem is restricted to the divide and conquer recurrence, okay, which will come up in the next stages, okay, in the advanced stages of this particular course. Anyway, therefore we will just keep it at bay. Okay, Master's theorem. But anyway, please be informed, my listeners are requested to be informed that there exist two methods. One is backward substitution method, other one is Master's method, and here we can apply backward substitution method very easily, and we will continue with Master's theorem wherever it is applicable. Okay, till then we will use only backward substitution method. Okay, so I will rewrite again, the basic recurrence relation that we have developed. It is number of multiplication. I will yet again explain this. Number of multiplications needed to find factorial of n equal to number of multiplication that is needed to find m of n minus 1 plus 1 multiplication. Okay, with a caveat or with a base case of m of 0 equal to 1. If input becomes 1, it goes on reducing. If it becomes 0, then you can readily find the answer. Okay, backward substitution goes on lessening the input one by one. Okay, by 1. Okay, m of n minus 1 can be expressed as m of n minus 2. Okay, plus 1 is it has to bring plus 1 once again. Plus 1, earlier plus 1 is also there. Therefore, it becomes 2. Once again, if you go for further, you will get m of n minus 3 plus 1 will come along with it. Okay, that is for 1 multiplication. 2 is already there, therefore 2 plus 1, 3. Okay, you cannot go on doing like this. It becomes a drudgery. You have to find a pattern. So I repeat once again, solving the recurrence relation involves applying applying backward substitution. When you go on applying the backward substitution, you will be lessening the input by 1 for almost all the problems, of course. You will be lessening the input by 1, and if you go on doing so, you will find at a stage, maybe in the third stage, maybe in the fourth stage, some kind of a pattern emerging. Here in the first step it is, in the second step it is 2 2 coming here, in the third step 3 and 3 is coming over here. Okay, you can replace this pattern by means of a variable. So therefore I will replace the pattern that is emerging by a variable, say k, by a variable k. So therefore it becomes m of n minus k plus k. Okay, now we will visit the base case, and we will see that this value within the bracket will reach the base case. Okay, so it has to become 0. It will become 0 if and only if we substitute k equal to n. Okay, substitute k equal to n. If you substitute k equal to n, what happens here is m of n minus n. M of n minus n is 0. Okay, this step I am telling about, plus n. Okay, so this will give us, m of 0 will give us, okay, m of 0 will give us 0, actually no multiplications as such, no multiplications here, sorry, it should be no multiplication. If input is 0, we are not going to multiply, we will directly return the answer. Therefore m of 0 equal to 0 plus n. Therefore number of multiplications while finding factorial of n is simply equal to n, and therefore this belongs to big theta of n. We may be surprised. Should we do such a drudgery as some kind of a analogy which went step by step into so many steps for finding efficiency case of such a simple problem? For this, the answer is no. Some of the problems, difficult problems, the solutions are based on only recurrence relation. Okay, this is the starting step, that's all. It's a simple example chosen in order to make our understanding very clear, and we will have some kind of a reinforced idea as to how we can obtain the efficiency case of a recursive problem. We'll take yet another example. Okay, this is raising an integer number to an integer power. Okay, something like a to the power of n. This can also be solved recursively. Okay, it is something like this. If n equal to 0, if the power is 0, then you will return 1. Okay, else you will return a into power of a n minus 1. N minus 1 should go on reducing, and a should go on multiplying. A and power of a comma n minus 1. Okay, I think we can write a very simple program over here. So power equal to 1. Okay, we will write a program and we will be able to understand very clearly. This is a repetitive kind of a program. So so power equal to 1 for I equal to 1, I less than the index, that is power, exponent less than or equal to, okay, let us say less than or equal to n, and I plus plus. This is the program, correct program. Then we will say power equal to, power into a. Okay, you can print a. Okay, this is exactly the program, and here it is translated into a recursive value, recursive kind of a thinking, and recursive kind of a solution. If n equal to 0, return 1. Okay, there is no question of multiplication. And if n is other than 0, the power is other than 0, you multiply a so many times, that's all. Power a comma n minus 1. So here the basic operation is 1. Okay, basic operation is multiplication. Therefore, basic operation n as a function of the exponent, that is n equal to basic operation, that is how many multiplications, as many multiplications as it is needed in order to find a power of a number to the power n minus 1 plus 1 multiplication, okay, before the function is called, and m of 0 equal to 1. Okay, m of 0 equal to 1, or m of 0 equal to 0. There is no multiplication involved. Okay, if the number is equal to 1 0, we will return answer to be 1. Therefore here no multiplications are involved. So similarly it goes just like factorial number, okay, factorial program or factorial algorithm. Therefore at the end what we get is m of n equal to n. So n terms, n multiplications are needed with a, with the base. If a is the base, okay, n times the base itself is to be multiplied with itself, okay, in order to raise that particular base to the power n. Okay, therefore this also pertains to, or this also belongs to big theta of n. Okay, so now what we have understood is develop a recursive algorithm. Okay, and before you do that, you have to determine the base case. Okay, determination of the base case is the gist of solving the problem in a recursive way. Okay, I repeat, finding the base case is the gist of, okay, solving a problem in a recursive fashion. Okay, once you found out, you will be getting the answer exactly. Okay, finding the base case would also amount to the lowest of the lowest input size and the answer and the corresponding value of the answer. Okay, therefore that is to be determined. Put up this base case as a condition. Otherwise the basic operation is to be done repetitively. Okay, multiplication is to be done repetitively or recursively with the reduced input size. Here the reduction in the input size comes in the form of the power, form of the exponent. Okay, now we will take up the famous problem of Tower of Hanoi. This problem is to be resolved or to be solved only by recursive equation. Okay, recursive kind of a problem solving procedure. The Towers of Hanoi puzzle, it is a puzzle, was invented by French mathematician Edouard Lucas in 1983. His invention has a story to go with it. There is a similar 3-peg arrangement at the Tower of Brahma in Benares, India. It is believed that in Kashi temple there are 64 gold discs, okay, packed one above the other. Okay, 64 gold discs stacked on 3 diamond pegs. Of course these three are pegs, diamond pegs. This can be called as A, this can be called as B, and this can be called as C. The world will come to an end. Okay, legend has it to say that when the priests of the temple move all the discs to the another peg, okay, from this peg to other peg, the world will come to an end. If the legend were true, and if the priests were able to move the discs at a rate of 1 disc per second, it would take 2 to the power of 64 minus 1 seconds, or roughly 585 billion years, or 10 to the power of 9 years to finish. Therefore it remains as a puzzle. Okay, another version of this legend is about monastery in Hanoi, Vietnam, where the monks, Buddhist monks, may make only 1 move per day. Okay, they are also moving the discs because they feel it is an auspicious thing to move discs, okay, from this peg to this peg, only one at a time, and this particular puzzle comes with a condition: only 1 peg is to be moved to this from here till here, making use of this empty peg or empty tower, whatever you say, and whenever we arrange the pegs, arrange the discs either over here or over here, care is to be taken to see that a bigger diameter disc is to be placed below a smaller diameter disc, or smaller diameter disc is to be placed above a bigger diameter disc. Okay, so we will find a solution for this recursive. Here there is only one kind of movement, solution, that is the movement of the discs. Okay, recursion means, dictionary meaning means same kind of things done repeatedly, Okay, here we will take this example in the form of a sketch, so it will be clearly understandable to us. Here is the problem comes with only 1 disk, n equal to 1. Okay, it is placed on A, peg A, and it can be directly moved to C without making use of this. Anyway, number of pegs, only 1 movement is required. Now number of pegs becomes equal to 2. Okay, now the way is you take the top disk and place it over here. Okay, so this disk is placed over here. Therefore this disk will become free and it can be directly moved over here. Okay, so this movement of this disk over here will have taken one movement, and this will have taken second movement, and this disk, the bigger disk, will have come over here and it is written over here, and the disk which was here will be moved over here. Okay, now all the two have been arranged, and it took three movements. First movement, the smaller disk to this tower, the bigger disk to this tower, so 1 2, and the disk which is over here should be moved over here. It becomes 3 because the problem essentially involves moving all the disks present in A to C, making use of B. Now we will make the problem little complicated by considering n equal to 3 disks. So let us see how to move about. This disk can be moved over here, this disk can be moved over here, so that involves 2 movements. Okay, when you move this disk over here and this disk over here, you can once again, okay, this disk comes over here, it is shown, and this disk is over here, okay, the small disk, and this small disk can be made to move over here, so it will occupy this particular position. In doing so, it will have involved 3 movements. Okay, 3 movements, that is the top two have been recursively moved, let us say recursively moved to this particular peg by making use of this particular peg. No, they are here now. Okay, in doing so it will have involved 4 movements, okay, 3 movements, and the bottommost disk will remain over here, and it will be aloof, it will be alone, it can be lifted directly and placed it over here. Okay, it can be directly placed over here. That involves the 4 movement. Problem is not still solved under stage T. So stage 3 brings in 2 disks placed in B and 1 disk placed in the bottommost disk placed in C. Okay, and then we can make the top disk to move over here, it will come over here, and then the bottom disk to move over here. So this is 5 and this is the 6th movement. This is the 6th movement. Okay, so by that point of time the arrangement will be like this. Okay, arrangement will be like this. This will have moved over here, this will have moved over here, okay, involving 6 movements, and now what remains is only 1 disk on A, and it can be directly moved over here. So it took 7 movements. For 3 disks it took 7 movements. Okay, here the basic operation is movements. Okay, the basic operation simply movements. So we will develop the recurrence relation something like this. Number of movements, I told you movements is the basic operation. Number of movements required for the transfer of n disks from peg A to peg C equal to number of movements required to transfer top n-1 disks from A to B making use of C. So when we took 3 disks, we saw that the top 2 disks, that is top n-1 disks, being moved to peg B by making use of C. Okay, and what remained is the nth disk in A, and it was directly moved. Okay, 1 movement to transfer the last disk that remains on A to C directly, and this is to be addressed. There are 2 disks, and therefore there are n-1 disks, okay, on B still lying. Okay, these n-1 disks once again should be recursively moved from B to C by making use of A. Okay, this equation you have to remember. Okay, it's very easy. Number of movements required for the transfer of n disks from peg A to peg C equal to number of movements required to transfer the top n-1 disks, 2 in case of 3. In case of 3 disks, top 2 disks, okay, n-1 disks from A to B making use of C, and 1 disk remains. Even if it is n, only 1 disk will remain, and that disk can be directly moved to C, okay, by making use of, it can be directly moved. And what remains, the problem remains unsolved once again because B contains n-1 disks still stacked. Okay, and they can be moved once again by making use of empty tower A to C. They can be moved recursively to C. Therefore, number of movements, okay, involved in placing n disks from A to C equal to number of movements that is required in order to place n minus 1 disks from A to B, okay, A to B by making use of C, and directly moving the last disk from A to C, okay, and number of recursive movements required in order to move n minus 1 disks that are stacked on B to C, B to C, A to B, and number of movements required in order to move only one disk. That is the first example first figure that we chose to explain. Okay, number of movements required in order to move only one disk is only one. Directly it can be placed to C, from A to C. Therefore, n should be greater than 1. In order to define this problem, n should be greater than 1. Therefore, upon simplifying, mvn minus 1, mvn minus 1 can be made to 2 mvn minus 1 plus 1. Now, by backward substitution, we will just carry on with this. 2, you take out 2, and mvn minus 1 should be replaced like this only. So, 2 times mvn minus 2 plus 1. The earlier one will be there. You multiply this will become 2 square mvn minus 2 plus 3. Okay, 2 into 1, 2 plus 1, 3. Once again, the next step, 2 times mvn minus 3 plus 1. Okay, we are substituting only for this basic function. Okay, you should remember that. Okay, 2 times mvn minus 3, 2 square is already outside. Okay, 2 square into 1, that will give you 2 square. 2 mvn minus 3 is already there. This becomes 2 cube mvn minus 3 plus 7. The pattern is emerging, but somewhere it is obscure. It has become 7. You can here in the third step there is a 3 present here, there is 3 present over here, and 3 is missing over here. Therefore, we can adjust this by tweaking this. We can just see that 3 will also surface over here. 2 to the power of 3 mvn minus 3, and 7 can be written as 2 to the power of 3 minus 1. 2 to the power of 3 minus 1. Okay. Now, we will substitute a variable k for the pattern that has emerged. Okay, and it becomes 2 to the power of k mvn minus k plus 2 to the power of k minus 1. Okay, and now we should get this equal to 1. This should be 1. If it is 1, we will get only 1. 1 is the moment. Okay, number of moments required for one disk is only 1. So n minus k should be turned into 1. That can be done by substituting k equal to n minus 1. Therefore, 2 to the power of n minus 1, wherever k is there, we will substitute n minus 1. 2 to the power of n minus 1, mv n minus of n plus 1. Okay, if you substitute n minus 1 over here, minus is there outside. So, n minus n plus 1 plus 2 to the power of n minus 1 minus 1. So, n will get cancelled. We will be left with 2 to the power of n minus 1 mv of 1, 2 to the power of n minus 1 minus 1. Okay, 2 to the power of n minus 1 plus 2 to the power of n minus 1 minus 1. Okay, upon simplification, because this will give you 1. Therefore, 2 into 2 to the power of n minus 1. Here is 1, here is 1. 2 to the power of n minus 1 minus 1. So, 2 to the power of n minus 1 into this has an index 1. Okay, indexes can be added. So, n minus 1 plus 1. It remains to be n 2 to the power of n minus 1. Therefore, the complexity or efficiency case of Tower of Hanoi is me moment of n, the basic operation is moment, belongs to theta, big theta of 2 to the power of n, and this is an exponential complexity case. Okay, in order to identify a complexity case to be exponential, the base should be a constant and the index or the power should be a variable. Okay, therefore we can substitute the values over here. If disks are 2, it took 4 moments. So, 4 minus 1 moments, that is 3 moments. If the disks are 3, it is 8 minus 1, 7 moments. If the disks are 4, it becomes 15 moments. Okay, 15 moments. We could not have afforded to write a sketch if we have chosen n equal to 4. Okay, it would have consumed a lot of time. Okay, therefore it is a exponential case. Now we will revisit the first problem that we chose, which is nothing but finding number of bits required to represent a decimal number. Okay, that was the starting point for us, and with this problem, this algorithm was real significance. It was very significant because this algorithm gave us a motivation for writing recursive algorithms, because we could not write we could not count number of basic operations over there, because every time the input is getting hard, we said over there. So if n equal to 1, return 1, else return number of bits equal to floor of n by 2 plus 1. So this count, this is getting added over here only. Okay, before we call the function, okay, number of additions, there will be one addition. Okay, addition is the basic operation over here. Okay, as you can see, addition is the basic operation over here, and therefore we will develop a recursive relation. Okay, number of additions required in order to find number of bits to represent a decimal number n equal to number of additions, as many additions as it is required in order to find number of bits for floor of n by 2. I repeat, okay, number of additions which is needed in order to find floor of n by 2, okay, plus 1, okay, for n greater than 0, greater than 1, of course, and if the value of the input happens to be 1, then there is no question of addition, because it returns directly the answer, returns 1, therefore a of 1 equal to 0. Okay, there is no additions if the input value becomes equal to 1. Okay, now we can apply backward substitution with a little modification, because backward substitution would stumble if ratio is involved. And to be specific, the ratio here, the n should be expressible as 2 to the power of k. Okay, then we can just directly apply backward substitution. So I repeat, whenever in a recurrence relation ratios are involved, ratio is, once again, it is a reduction in the input size, successive reduction in the input size. For example, n by 2, n by 4, n by 8, n by 16. That is the order in which the input is reduced in successive recursive calls. Okay, that is a reduction happens by ratio. Okay, anyway, we cannot directly deal a ratio while we try to solve these equations of recurrence, and there is a method called as smoothness rule. Okay, we need to apply smoothness rule. This ratio is to be smoothened. Yes, smoothness rule, you have to remember this. Okay, smoothness rule is not very hard to remember. Smoothness rule will smoothen this particular ratio by assuming n to be expressible as some 2 to the power of some integer power, 2 to the power of k, let us say. So n is expressed as 2 to the power of k. Therefore I will substitute over here. So in place of n I will substitute 2 to the power of k, and here it is a of 2 to the power of k minus 1. Okay, 2 to the power of k minus 1, 2 to the power of k divided by 2 to the power of 1, it will come up and it will become lessened by 1, 2 to the power of k minus 1 plus 1. So we will take on to backward substitution. This will become a 2 to the power of k minus 2, okay, k minus 2 plus 1 plus 2. Yeah, 1 is already there. Okay, and if you go further, it is a 2 to the power of k minus 3, 2 to the power of k minus 3 plus 3. Okay, plus 3. There goes this thing, and a pattern is found. It is a 2 to the power of k equal to, okay, a 2 to the power of k minus I. Okay, that pattern is replaced by a variable I. Okay, the 3 is replaced by I. In the fourth step it would have given us 4, and here also 4. Like this, there is a pattern emerging, plus I. Now we have to take this to a base case. The base case happens to be 1. The base case happens to be 1. Okay, it should become 1. So when exactly it will become 1? If you substitute I equal to k. If you substitute I equal to k, put I equal to k, I will write over here. If you put I equal to k, what happens is a 2 to the power of k minus k plus k. Okay, 2 to the power of k minus k is 2 to the power of 0. That will give us 1. Therefore number of additions equal to 0, and what remains is k. So now we have come to a stage wherein we will be able to solve this recurrence relation as a 2 to the power of k equal to k. Okay, we have assumed, our assumption went like this: n equal to 2 to the power of k. N was expressed as 2 to the power of k. Therefore, by base exchange formula of logarithm functions, k will be definitely log n to base 2. Okay, can the listeners, respected listeners, are supposed to go through the basic foundations of mathematics, wherein logarithmic functions are discussed. Okay, this is called as base exchange formula. If n equal to 2 to the power of k, then k equal to log 2 of n. Therefore, I will just substitute over here a of n once again, because 2 to the power of k is replaced by n, and k will be replaced by log 2 of n. Okay, log 2 of n. And exactly speaking, if a number is cannot be expressed as 2 to the power of k, if it is 15, let us say, this log 2 of 15 will give us a fractional value. Let us say 15 will give us 3 point something, and we have to reduce it to 3 by applying floor, and we have to add 1. Okay, therefore the real formula happens to be log 2 of n plus 1. Of course, floor over here. Therefore, number of digits required to represent a decimal number of digits in d equal to log 2 of n plus 1. Okay, this is the formula. But anyway, by efficiency analysis, we got down to this particular solution. Okay, a of n equal to log 2n. Therefore, this falls to efficiency case of big theta of log 2n. And we are also taken to understand, whenever division of input is involved, if it is divided by 2, then the efficiency case comes out to be a logarithmic function. If it is divided by 3 in some other problem, it will become log n to base 3, something like this. Okay, so this is very peculiar of a recursive function. Okay, recursive algorithms. Okay, and this is of the finest kind of a solution procedure, because the number of steps, number of additions reduced to log n to base 2. Okay, right. And I have given some problems over here. Please, my esteemed listeners will be definitely venturing into that, and they will be able to solve upon listening to this lecture. Okay, write of course, hint is also given. Write a recursive algorithm to add 2 integers. Hint: if a becomes a plus 1, b will be reduced. Okay, a goes on increasing, b goes on reducing. That's the way you can recursively add a and b. When b becomes equal to 0, then you will be returning a as the answer. Okay, this is recursive addition of 2 numbers, 2 integers. And recursive algorithm for linear search, you have to set forth the linear search. You have to set forth the initial values of the lower bound and upper bound, the left extremity of the array and right extremity of the array. If left is lesser than r, if array of L equal to key, return 1, there is only one comparison. Else L equal to L plus 1, okay, lower bound equal to lower bound plus 1, linear search, array L comma R and key. So upper bound, lower bound, the lower extremity is taken in this direction. Okay, therefore it will reach, finally it will become one element, okay, by successive iterations. Okay, otherwise if it is not found, it will return 1. You just modify this, okay, with a small tweaks, and you will be able to write the algorithm. And some problems are also given. These problems are of academic interest. Okay, you can solve these recurrence relations. Okay, this is f of n minus 2 plus 6 plus 6, or 2 times 6. F of n minus 3, 3 times 6. So the pattern emerging. 5f of n minus 1. Okay, 5 into 5 f of n minus 2. So 5 square f of n minus 2. 5 cube f of n minus 3. So pattern is emerging. And look at the base case and carefully do this. F of n by 2. Similar to this, n is expressed as 2 to the power of k. Then go on applying backward substitution method and find the solution for this. So in this tutorial we addressed how to write algorithms, recursive algorithms, and how to analyze them for their efficiency case. Okay, and we have understood that a recurrence relation is to be framed, and upon framing the recurrence relation, which is nothing but an equation with a lower bound, with a value as to when the calling of the function again by itself will be stopped. That is the base case. And we have also told identifying the base, if you identify the base case for any recursive problem solution, half the war is won, because you will be knowing the exact value of the input where solution is found, and you will be reducing the input, a bigger input up to that particular stage. While doing so, you will find a pattern and you will substitute the pattern by a variable, and you will drive that function involving this variable and the input, reduced input, to the base case. Thus you will find the solution and you will solve the recurrence relation, and upon solving the recurrence relation you can directly write the efficiency case. Okay, with this I think we have made it, I have made the things clear, okay, to our esteemed listeners, and they will listen to this again and again, and they will become conversant in solving analyzing recursive kind of algorithms to determine its efficiency case. Okay, and before we take up next chapter or next module or next concept in design and analysis of algorithms, until then